Satellite internet has revolutionized how we connect to the digital world, and at the forefront of this transformation stands Starlink, SpaceX's ambitious project to provide high-speed internet access globally. Today, we're diving deep into the fascinating technology behind how Starlink actually works, from the pizza-sized dish on your roof to the constellation of satellites orbiting Earth at mind-boggling speeds. Let's start with the basics. Starlink's system consists of three main components: the user terminal, affectionately nicknamed Dishy McFlatface, the satellite constellation, and the ground stations. Unlike traditional satellite internet that uses a few satellites in geostationary orbit at 35,786 kilometers above Earth, Starlink operates in low Earth orbit at around 550 kilometers. This closer proximity is crucial for reducing latency, but it creates unique challenges that require innovative solutions. The heart of the system is Dishy McFlatface, a remarkable piece of engineering that looks deceptively simple. Inside this sleek dish is a phased array antenna system containing over 1,200 tiny antennas working in perfect coordination. These antennas can electronically steer the beam of data without physically moving the dish, which is essential because Starlink satellites zip across the sky at about 27,000 kilometers per hour. The technology behind this beam steering capability is fascinating. Each antenna element in the array can adjust the phase of its signal independently. By carefully controlling these phase differences, the dish can create constructive interference in the desired direction and destructive interference elsewhere, effectively forming a focused beam of data that can track satellites as they move overhead. But how does the dish know where to point its beam? This is where Starlink's sophisticated software comes into play. The dish contains a GPS receiver and computing hardware that constantly calculates the positions of nearby satellites based on their known orbits. It then coordinates the phase adjustments of all antenna elements to maintain a solid connection, switching between satellites approximately every few minutes as they pass in and out of view. The data transmission itself occurs in the Q and Ka frequency bands, typically around 12 to 18 gigahertz. At these frequencies, the signals can carry massive amounts of data but are also susceptible to atmospheric interference, particularly from rain and snow. To combat this, Starlink uses advanced signal processing and error correction techniques, along with adaptive power control to maintain reliable connections even in challenging weather conditions. The satellites themselves are technological marvels. Each one weighs about 260 kilograms and is equipped with 4 powerful phased array antennas. 2 of these antennas communicate with user terminals on the ground, while the other 2 maintain links with neighboring satellites. This inter-satellite communication capability, enabled by laser links, allows Starlink to route data through space instead of relying solely on ground stations, reducing latency and expanding coverage to remote areas. One of the most impressive aspects of the system is its ability to handle multiple users simultaneously. Each satellite can communicate with multiple user terminals at once, dynamically allocating bandwidth based on demand. The satellites use time division multiple access, TDMA, and frequency division multiple access, FDMA, techniques to manage these connections efficiently. The ground stations, often overlooked but crucial components of the system, serve as the interface between the Starlink network and the traditional internet backbone. These stations use large antennas to communicate with passing satellites, routing traffic to and from the internet. SpaceX has deployed hundreds of these stations globally to ensure comprehensive coverage and redundancy. The entire system operates autonomously, with sophisticated collision avoidance systems built into each satellite. Using their ion thrusters, the satellites can adjust their orbits to avoid space debris and maintain optimal spacing within their orbital planes. This autonomous operation is essential given the scale of the constellation, which will eventually include tens of thousands of satellites. What makes Starlink particularly revolutionary is its ability to provide high-speed internet to areas where traditional infrastructure is impractical or impossible. The system can deliver speeds exceeding 100 megabit per second with latencies under 20 milliseconds, comparable to many ground-based broadband services. This is achieved through a combination of the low orbital altitude, advanced signal processing, and the massive parallel processing capability of the phased array antennas. The user experience is remarkably simple, despite the complex technology working behind the scenes. Setting up Dishy McFlatface is nearly plug-and-play. The dish automatically orients itself, finds satellites, and establishes a connection. The accompanying app provides real-time statistics and helps users optimize their dish placement for the best possible signal. Looking to the future, SpaceX continues to improve the system. Newer satellites include enhanced capabilities, such as improved laser inter-satellite links and more efficient propulsion systems. The company is also working on reducing the cost of the user terminals while increasing their performance and reliability. The implications of this technology extend far beyond just providing internet access. Starlink's success has demonstrated the viability of large satellite constellations for global communications, paving the way for future innovations in space-based services. It's also driving advances in areas like phased array antennas, satellite manufacturing, and autonomous space operations. The environmental impact of such a large constellation hasn't been ignored. SpaceX has implemented several measures to minimize space debris and reduce the impact on astronomical observations. These include designing satellites to be fully demisable upon re-entry and equipping them with autonomous collision avoidance capabilities. As we wrap up this exploration of Starlink's technology, it's worth reflecting on how this system represents a convergence of multiple cutting-edge technologies, from advanced materials and electronics to sophisticated software and autonomous systems. It's a testament to human ingenuity and our ability to solve complex engineering challenges, ultimately bringing us closer to a future where high-speed internet access is truly universal. The success of Starlink has already inspired other companies to pursue similar satellite internet constellations, suggesting that this technology will continue to evolve and improve. As these systems become more sophisticated and accessible, they have the potential to bridge the digital divide and connect billions of people to the global information network, fundamentally changing how we communicate and access information in the 21st century.